Introduction to Computer Controller Processes, Part 3. Yesterday, at the time of completion, we have seen that how to discretize a PID controller. Let us once again see that. To how process variables are represented in discrete domain. Suppose now we are starting to monitor the process variable at the 0th sampling instant. You will get a value of y of 0, y1 first sampling, y of 2, etc. Like that, you will get process variables. Then what is set point? Set point also a constant analog value, but if you see this as discretized value, then set point of 0, set point of 1, like that we will get. Then what is the value of y at the nth sampling instant? The value of process variable at the nth sampling instant is ynT, where t is the sampling period, n is the sampling instant. Similarly, the y set point is set point for y, that is y set point is y set point of nt. Nth instant, general case. If you put n equal to 0, you will get the first value. N equal to 1, you will get the second value, like that. So you have these two in your hand. How to find error at the nth sample instant, ynT, where t is the sampling period, equal to y set point minus yn of t. You will get error. Then we know that the expression for PID controller in continuous domain is m of t equal to m of t equal to kc multiplied by m of, e of t in continuous domain, e of t plus kc upon ti multiplied by the integral of e of t dt plus derivative term kc td multiplied by de of t by de of t by dt. This is expression for PID controller in continuous domain. So now we got E of t in discrete domain, that is En of t. If you substitute here, this m of t becomes n of t equal to kc multiplied by En of t. That's all. This is only proportional controller. Similarly, for integral controller, we have to multiply that kc by ti, instead of this integration becomes summation. In discrete domain, this integration becomes summation of e of kt. But we have to integral means, suppose integral means this is the error signal, e of t, this is e of t. If you integrate, you will get area under this graph. That is, this is time, that is e. If you plot, if you integrate from t equal to 0 to t up to this instant, if you integrate, you will get if you integrate, you will get area under this error graph, you will get. Similarly, if you separate this in terms of strips, so this strip, first strip indicates that its rectangle is equal to first sample e of 0, and the second sample, its length is e of 1, E of 1. Third rectangle, its height is E of 2. Like that, I have some rectangle. I separated this graph into rectangles. Each rectangle has a width of sampling period T. So if you multiply E of 0 with the sampling period, you will get area under this. So if you multiply E1 multiplied by sampling period, you will get area under this. If you add all the rectangles, area of all the rectangles, you will get area under this graph. That is the idea. So all the before summing all these, you have to multiply this by sampling period. It's common for all errors. That's why we can take that in outside. So Kc sampling period divided by Ti in discrete domain, sum of E of Kt. K should vary from 0 to n, present sample. K equal to 0 to n. When n equal to 0, the first error, up to n, we have to add all the errors. Then you will get the PI controller. How to get PID controller? We have to find d by dt. What is d by dt? D by dt is, we have to find de by, in the top I am writing, de of t by dt can be approximated to delta E of t by delta t, delta t. This is infinite small. D by dt is infinite small changes in both. This is changes in E of t. That can be written as change in E of t is what? E of n tau, E of n tau minus E of n minus 1 t sampling period. Sampling, not tau, t sampling period. So E of n minus E of n minus 1 t. Numerator I got. What is denominator? This is present sample. This is previous sample. What is the difference between the time for this t? Therefore, we can write d by dt can be written as E n of tau minus E n minus 1 t divided by t, where t is the sampling period. That's why here you will get Kc Td. Td is derivative time divided by sampling period t. This t is common. Multiplied by E of n tau minus E of n minus 1 t sampling period t. So this is the expression for discrete PID controller. So how to implement this? Suppose at the nth sampling instant, at the 0th sampling instant, I want to find the controller output. Put n equal to 0. At the first sampling instant, what is the controller output? Put n equal to 1. Like that, if you substitute, you will get the controller output. That will be sent to the process through DAC. Yesterday, we have seen what is the function of DAC. DAC will convert this sampled value into continuous signal. So, this is the expression for discrete d by dt. D by dt is E n of tau minus E n minus 1 of tau divided by tau. Similarly, integration is how that integral can be written as t times y. All strip has a width of t. Each strip has a width of t. Each strip has a width of t. Therefore, t common. Sigma k equal to 0 to n, because up to n we have to find E of n tau. That's all. So this is integral of E of tau. So this way we can convert continuous time PID controller into discrete time PID controller. Now we are entering into Z transform, Z transform. Already we know that Fourier transform, then Laplace transform, and Z transform. Fourier transform, Laplace transform, Z transform. There are 3 transforms are there. You can notice that Fourier transform is not used in controller. Why? Fourier transform is not used in control system, process control, computer control of process. We are not using this Fourier transform. We are using this Laplace transform and Z transform. One of the conditions to get the Fourier transform of any time function is it should be integrable. All integrable functions alone can be, we can find, alone can have Fourier transform. Can have alone can have Fourier transform if it is integrable function. But in control system, we are studying about stability. So that's why unstable system also will come into picture. Stable as well as unstable system. If you integrate the output signal of an unstable system, that is not integrable. Its output you will get infinity. So it is not integrable. That's why the unstable systems we cannot bring under Fourier transform. So we won't use Fourier transform in control system. We'll use Laplace transform and Z transform. Why? How Laplace transform can be used? Because in Laplace transform, suppose I'm having a signal which is going like this. It is unstable system. Here it is going like this. It's go on increases in both sides, exponentially increasing signals, exponentially increasing signal. For that you cannot find Fourier transform. But in Laplace transform, what we are doing is we are multiplying this signal by a exponential signal. Exponential. This part is truncated. Since we are multiplying this by exponential signal e power minus s tau, this part is truncated. This is e power minus s tau. This unstable part is truncated. We are having only dynamics of unstable system. Dynamics alone we are having. That's why we can take Laplace transform. Because the transformation for both Fourier and Laplace are almost identical. Integral of that function e power sigma plus j omega for this the function f of t multiplied by e power minus st integral of both are almost identical. Then how we can find for this because of this e power minus st, it is multiplied by a exponentially decreasing stable function. It goes to 0 as t tends to e power minus st. We are multiplying by e power minus t. As t tends to infinity, this function becomes 0. Therefore, we are truncating the unstable part, and we are finding the transform. That's why always we are using Laplace transform in control system. Then it cannot be used for discrete, because for discrete time system is also a special form of Laplace transform is Z transform. So Z transform also a Laplace transform, but a special transformation. So this is for only discrete signals, sampled signals. All sampled signals we can go for Z transform. If it is continuous signal, we can go for Laplace. For all sampled signals, we are going for Z transform. Now, how to find Z transform, that we will see now. Before that, the Z transform maps a discrete time signal from time domain to Z domain, Z domain. So how Laplace transform transforms time domain, continuous time domain to S domain. Similarly, Z domain transforms time domain into Z domain. Time domain into Z domain. It transforms time domain into Z transform. Z transform. This is Z transform. Transforms this time domain into Z domain. Z transform of a given function depends on the selected values of sampling period t. This is that's why once you take Z transform, we do not know the sampling period. We do not know. Suppose I am sampling two signals. One is unit step function. I am sampling at this instant, at this instant, at this instant. Definitely, if you sample a unit step function, up to infinity, it will be the same magnitude, say unit step function. So its value will be always 1. Sampled value is 1. I'm having a unit amplitude sinusoidal signal. Here also I am sampling at whenever a positive peak occurs, I am sampling. So I'll get 1 again. Here also I'll get 1 again. Here also I'll get 1 again. If you find the Z transform for both, you'll get the same value. You'll get the same Z transform for both sinusoidal as well as step function. From that, we can understand that we are finding Z transform is giving doesn't reflect the original signal. Instead, it reflects the sampled values of original signal. It reflects the sampled values of original signal. If it is poorly sampled, it won't represent the Z transform won't represent the actual signal. Instead, it will represent some other signal. This is example. If we are sampling every t seconds, both gives 111 value, then definitely both give the same Z transform, even though the both signals are different. That is one important point. Then um, two distinct functions. One is sinusoidal signal, another one is step function, another one is step function. Two distinct functions have the same sampled values at the sampling instance. They also have the same Z transform that we have seen. Cannot be distinguished. Once Z transform is obtained, it cannot distinguish the two function. Consider the step function and a cosine wave sampled shown in figure. The values of two functions at the sampling instant all are one, both are one. If it is cosine function or step function, always it gives 1 1 1. If you find step function as well as cosine function, it is nothing but 1 by 1 minus z power minus 1. So from this, for both functions, it gives a step z transform. That's why we cannot distinguish once it is Z transform is obtained. We do not know the value of T also. From the Z transform, T, we do not know. What is the value of T is unknown. T is unknown. From Z transform, we cannot find the value of T. T is unknown. That is very, very important. If you give any transfer function, what is T? We do not know. T, it is independent of. In other words, Z transform is expression is Z transform expression is independent of T. T won't appear here. And this is a transform. Then Z transform exists only for those values of independent variable Z for which the summation of infinite series is definite value. In Fourier transform, integral of E of t, sorry, integral of f of t, some function. For that, I am going to find Fourier transform. Bilateral means minus infinity to plus infinity. Unilateral means 0 to infinity. F of t dt minus must be finite for Fourier transform. Similarly, for Laplace transform, this and the product of e power minus st must be finite. In Z transform, we are getting sequences. We are getting sequences, infinite sequences, sampled values. We are getting sampled values. If you add them, if you find the sum of the series, it must take a finite value. If you add all together, it must give a finite value. Then only we can find find that Z transform. Next one is we know that sampled signal can be written as n equal to 0 to infinity, because this y value has infinite values. If you substitute n equal to 0 to infinity, you will get infinite number of values. But at what instant the delay is represented by e power minus nts. The delay is represented by e power minus nts. If you substitute n equal to 0, no delay. If n equal to 1, the signal appears. If n equal to 0, the sample is here at t equal to, let us define this in continuous domain. Here it is sampled. N equal to 1 means after one sampling instant at one sampling instant. That is after a sampling period of t, this first value is sampled. n equal to 2, it is sampled here. It is sampled here. That is the meaning of this. This can be represented in S domain. If you substitute e power ts equal to z, the same expression can be written as sigma n equal to 0 to infinity y of nt z power minus n, z power minus n. So in z transform, in Laplace transform, if you substitute z equal to e power e power ts equal to z in Laplace transform, if you substitute e power ts, if you substitute e power ts equal to z, then it becomes z transforms. That is the meaning. This is the definition for unilateral z transform. N equal to 0 to infinity y of n tau z power minus n y of z. Therefore, y of z is infinite series. It is multiplied by z power minus n. Infinite series multiplied, infinite sampled values. We can say like that. Infinite sampled values multiplied by z power minus n is z transform. Now let us find z transform of basic functions. What is z transform of what is the z transform of unit step function? To find z transform of unit step function, its value is 1 by 1 minus z transform of unit step function is 1 by 1 minus z power minus 1, or z upon z minus 1, z upon z minus z upon z minus 1. Both way we can represent. The unit step function can be written as if you sample, this is the unit step function. It's always unity. Unit step function. I'm not able to draw horizontal line. This is value is at the 0th instant 1. At the first sampling instant, its value is 1. Second sampling instant, its value is 1. Third sampling instant, it is 1. So 1 first sampling instant, second sampling instant, third sampling instant, etc. So how to represent this? This can be represented by e power minus n t s e power n t s multiplied by 1. This signal, how to represent n equal to 1 in this case, so no need of n. Here how it is represented, its value magnitude is 1 after a delay of e power minus 2t, 2 sampling period delay. Yes, 2 ts. But if you substitute z equal to e power ts, then what you will get is z power minus 1 for this. You will get z power minus 2, etc. It is an infinite series. If you add this geometric series, you will get 1 by 1 minus z power minus 1. If we add this up to infinity, you will get 1 by 1 minus z power minus 1. Therefore, the z transform of unit step function is 1 by 1 minus z power minus 1, provided this is true only when z power minus 1 must be less than 1. Modulus of z power minus 1 must be less than 1, which makes the series convergent to finite value. Then only it will be. If it is not less than 1, it won't converge. That's why it must be less than 1. Then z transform of a exponential function. Exponential function is e power minus at. So the delayed hereafter the delayed function will be represented by z power minus 1, z power minus 2 delayed by 2 sampling period, z power minus 3, etc. How it came in Laplace domain, delay is represented by e power minus n TS. It will be, it means the delay by n sampling instant. That is the meaning of delay. But Z transform is special case of Laplace transform when e power ts equal to z. Therefore, z power minus n it becomes. Since e power minus st equal to z, therefore any delay is represented by z power minus 1, minus 2, minus 3, a special case of Laplace transform. So e power minus at, e power minus at, for that we have to find z transform. The value is 1 by 1 minus e power minus at z power minus 1, that we have to prove. For that it can be written as a infinite series when e power at at the first sampling instant n equal to 0 to infinity e power minus a n t z power minus n. So this is to represent the delay, delayed sampled values. So this can be easily proved that 1 by 1 minus e power minus at z power minus 1. Similarly, and this is also a geometric this e power, you bring that e power a n combined with this at combined with this, write a whole power n like that. It can be written as e power a at z whole power minus n. So you see previous here z power minus 1, instead of z we are having e power minus e power at z. That's why wherever you find z, it is replaced by e power at z. That's why I said it is very simple to prove. So instead of you substitute this as z dash, then you will get in terms of z dash, replace z dash by e power at z, you will get this derivation, exponential function. So ramp function is at z power minus 1, 1 minus e power z power minus 1 whole square. What is ramp function? Ramp function is this. If the slope is unity, the slope is different, slope is a, means you'll get like this. A slope is a, means this a represents the slope. This is a ramp function. Ramp function with respect to time, continuous. You have sampled values for that ramp function. You have the sampled values for that ramp function. You can write that sampled values as a tau z power minus 1, 2a tau z power minus 2, 3a tau. This is the n varies from 0 to infinity. You will get all this. So in all terms, a and t are common. That's why that can be taken outside. So it can be written as like this. In addition to that, at is taken outside, and z power, this is first term is 0 because this is the first time we are getting the first term. First term is 0. That's why sum of the series is 1 by 1 minus z power minus 1 whole square. So two terms already you are having. If you take that, you will get at z power minus 1 upon 1 minus z power minus 1 whole square. This will exist again, the same condition. The modulus of z power minus 1 must be less than 1. Trigonometric functions. If you want to find z transform of trigonometric functions, that is also possible. This is the z transform of sine omega t. This is z transform of cos omega t. Euler's theorem says that sine omega t, it can be written as in sampled domain. Sample domain is sine omega t is continuous domain. In sample domain, it can be written as n equal to 0 to infinity sine omega nt z power minus n. This z power minus n, why? To represent delay. That already we have seen. So this represents each sample. Now if you now if you apply Euler's theorem, you will get sine omega t equal to e power sine omega t equal to e power j omega t minus e power minus j omega t uh, upon 2j. This if you apply that, you can write like this. You can write like that, and z power minus 1. Already we know the z transform for e power at. By using that, you can find and simplify. Again, replace this 1 by 2j is outside. If you combine this and this, you will get sine omega t in the numerator. If it is cos omega t, there is no j. There is no j here. The same thing, but divide by 2. There is no 2, that's why 2 times multiply and divide by 2. You will get 2 cos omega t is at power minus 1. If you take this one and this one is sine omega t. This one is here. Sorry, this one is here. And if you take multiply this by z, numerator and denominator by z, you will get this expression. This expression. If we multiply the numerator denominator by z, you will get this expression. Or you can take that, yes, you will get this expression. Already we know that how to find z transform for e power minus at. That is used here to find z transform for sine omega t. In the same way, you can prove that cos omega t equal to this. Cos omega t equal to this. You have to apply that Euler theorem to transform this in terms of exponential function. Translated functions. How to find z transform for translated function? Translated means delayed function. Here, this is here. This is the original signal. If you delay this original signal by td times, td seconds, then signal will be like this. Delayed signal by td seconds. The td equal to 1 sampling period. Td equal to 1 times sampling period. So here the signal is advanced. This is another example. Is the signal, if comes here advanced, it comes before that. So the signal is nt plus 1t. Here nt minus t. Delay by 1 sampling period means f of nt means present value delayed by 1 sampling period. 1 sampling period, it can be represented like this. If it is advanced signal like this, here f of nt plus t, like that will represent. Therefore, z transform delayed function means we know that any delay can be represented. Td equal to kt. Td equal to kt. We are not keeping the delay as such. Instead, we are finding how many delay is equal to how many times sampling period we are finding. Delay is taken as how many times multiple of sampling period. This is k times sampling period. This delay equal to k times sampling period. That's why it can be written as e power minus n kt, e power minus kt n, yes, it comes. Z transform of a delayed function f of t minus td, that is equal to f of t minus kt. Td is written as integral multiple of sampling period, that is t minus kt. Now how to write this as a sum of sampled values n equal to 0 to infinity, f of n tau minus kt minus kt. Each signal is delayed by a uniform delay. This sample is delayed by the same amount, same amount. This is also same amount. Each is delayed by kt, z power minus n. Now to find this, let us substitute nt minus kt. If you take t outside, you will get f of n minus k multiplied by t. You will get uh, uh, n minus k. If you substitute n minus k equal to L, you will get f of Lt. Let us assume that it is 0 for negative values of L. Then we can write nt minus kt z power minus n can be written as f of Lt, because n minus k equal to L. And now n becomes what? L equal to n minus k means what is n? N equal to L plus k. Here minus n, that's why minus L minus k. This k can be taken outside. Therefore, if, it is independent of L. Here the index is L, not n. Instead of n, we are having L as index in that Z transform. So you can take this Z power minus k outside, so that f of z power minus k. So any function that delayed by k sampling period means z power minus k f of z. There is no change in the z transform. Only thing is the z transform of undelayed function multiplied by z power minus k. These are all z transform of various functions. So what is z transform of unit impulse function Laplace transform? 1. In z transform also 1. Unit step function in Laplace domain 1 by s. In z domain 1 by 1 minus z power minus 1. The ramp function is a upon s square. Here already we proved this. A tau at z power minus 1 upon 1 minus z power minus 1 whole square, like that. Similarly, we have proved this also, SineOmegaT also. So these are all the important Z transforms you need while studying computer controller process. If you remember all this, it will be better. Now, properties of, we are not going to see all properties. What are all important for computer controller process, that only we are going to see. Linearity is the transform of sum of two functions equal to is the transform of individual functions. That is that's why it is it satisfies the linearity property. So a1 f of 1 plus a2 f of 2, if we take z transform, then what you will get, infinite sum of n equal to 0 to infinity a1 f1 of n tau plus. We know that summation can be separated. Summation, this and this can be applied inside. Then you will get these two separate z transforms. A1 is z1 f1 z transform of f1, a2 is the transform of f2. That is equal to a1 f of f1 of z plus a2 f2 of z. You will get final value theorem. What is final value theorem says? What is the advantage of final value theorem? In z domain, if you multiply the function by z power z minus 1 and let z tends to 1, you will get x of infinity. Time domain value, you will get time domain value. This is time domain value. Time domain value you can get from z domain value. That is the advantage of final value theorem. No need to convert the z domain function into time domain, and final value there you can find. But instead of doing that, you can get the final value. Uh, you can get the final value in z domain itself, but the value given is for time domain. So you can find x of infinity. You can find x of time domain x of infinity from z domain. That is the advantage of final value theorem. What the final value theorem says? X of infinity equal to limit z tends to 1, z minus 1, x of z. That's all. This plus here indicates it is unilateral. It is true only for right hand side. Those things you don't worry. So you take it as x of z. So now let us consider this function. To prove this, we are taking this z transform of x of n plus 1 minus z transform of x of n. We are consider this. Consider, to prove this, consider this function. Then we know that this is x plus 1. Let us assume that sampling period equal to 1. Then it is future value. Future value means what is the z transform of um, time shifted function, shifted by m equal to 1. In this case, the z transform of this is equal to z transform of z into x of z minus z into x of 0. This is the z transform of time shifted function. So z multiplied by, this is not z transform, z multiplied by z x of z minus z multiplied by z x of 0. This is the from the known property we can write like this. And what is z transform of x of n? That is x of z. So now there are two x of z that can be grouped. So if you group two x of z together, you will get for this the coefficient is z, for this the coefficient is 1. That's why z minus 1 x of z you can write. This z into x of 0 you are writing here. The right hand side for this you can write that limit k tends to infinity. Now I am changing the index by k, n equal to 0 to k tends to infinity. What is um, z transform here? Instead of k, if you put z transform, that is z transform. But I am introducing one more variable, k, by assuming k tends to infinity. So x of n plus 1 minus x of n z power minus 1. That is z transform. Expression for is the expression for z transform is written like that. Instead of putting infinity here, I am writing limit k tends to 0. That is the only difference. So you are keeping limit instant k tends to infinity as such. You are writing the expression. You are varying n from 0 to k. What you will get? X of 1, x of 0, x of 2, x of 1, like that. What you are doing is you substitute n equal to 0, x of 1, n equal to 0, x of 0. That is the first term. Second term, n equal to 1, 2, 1, the second term. Like that you are writing. So this is an in up to k you are writing. This and this getting cancelled. This and this getting cancelled. This and x3 getting cancelled. All getting cancelled except all. If you cancel this, one term is here. If you cancel this, some term must be here. So except this will be getting cancelled from the previous, but except this all are getting cancelled. So now if you limit, let k tends to infinity, what you will get is x of infinity minus x of 0. The two terms are this and this are not getting cancelled. Therefore, if you substitute, let k tends to infinity, x of infinity minus x of 0 you will get. Now take limit on both sides. Z tends to 1. What is in the right hand side? You are having z power minus n is there. Z tends to 1 means 1 to the power minus n, that is equal to 1. So if you apply limit z tends to 1 on both sides, here you have one z, that becomes 1. Therefore, here you will have x of 0, the left hand side. Right hand side also you are having x of 0, because z power minus n equal to 1, because substituting z tends to 1. Therefore, both side you are having x of 0 getting cancelled. Therefore, x of infinity equal to limit. Here we are not taking limit. If we take limit, this term vanishes. That's why we are writing limit is limiting case. It is not equal. Limit z tends to 1, z minus 1, x of z. If you substitute that, you will get x of infinity equal to limit z tends to 1, z minus 1, x of z. So this is final value theorem. You can find the final value in time domain from z domain itself by applying this rule. No need to find the time domain function and find the final value. So steady state value can be find in z domain itself. The same way we found final value theorem for Laplace transform domain, Laplace domain also final value and initial value theorems are used to find the time domain values there. Initial value theorem. Initial value theorem says we can find the initial value x of 0 from time domain z domain expressions. We know x of z. We can find x of t as t tends to 0. So if you apply z tends to infinity for the z domain function, you will get x of 0. If x of z equal to z times of x of n, then you can find x of 0 simply letting z tends to infinity. That's all. So let us prove this. To prove that, we know that x of z is n equal to 0 to infinity, sigma n equal to 0 to infinity, sum of x of n, as n varies from 0 to infinity, multiplied by z power minus n. Expand this x of 0, z power 0, 1. So x1, x2, etc. like that. Now, allow z tends to infinity, what you will get is this term, if you z tends to infinity means z power minus 1 means what? 1 by z. Z tends to infinity means this becomes 0. What is the meaning of z power minus 2? 1 by z square. So if you substitute z equal to infinity, this also becomes 0. So all terms up to infinity become 0 except the first term. Therefore, you can apply limit z tends to infinity x of z equal to x of 0. So if you apply z tends to infinity on both sides, you will get the initial value. Inverse is the transform. You have analyzed a system by using Z transform. Finally, you got the output of the system in Z domain. How to find what is the output of the system in time domain? For that, we have to find inverse Z transform. It is to find take back the values in time domain. At the sampling instance, again we won't get time domain. Suppose I'm having a step function, I'm having a step function in Z domain. I'm having step function in Z domain. This is represented in time domain, the sampled values of u of t. I am having 1 by 1 minus z power minus 1. This is in z transform step function. If I take z inverse for this, what I will get is I will get these values. That's all. These values. It doesn't mean that it is taken from step function. It may be a waveform which always passes through this one. That's why already we have seen this point already. So it gives sampled values only. It gives sampled values only. It goes take inverse of result. You will get sampled values. That is y of 0, y of t, y of 2t. Like that, all sampled values will be given if you take z and inverse. That's all.